Oh yes, we're back. Today, lecture 22, we'll be talking about backtracking and branch and bound algorithms. We touched on them in a previous lecture about algorithm families. Now we're going to go a little bit deeper into this. We're going to look at the structure of these two algorithms, algorithm types, and see how we can use them to our advantage. And part of what Project 4 is going to be based on is using a branch and bound algorithm. So this is good, timely information. We'll cover some of the stuff we talked about in yesterday's lecture, constraint satisfaction problems and optimizations. Then we'll look at the general form of backtracking, and we'll look at a specific implementation of this with a problem known as n-queens. And then we'll go into branch and bound and see how that applies to the traveling salesperson problem. So backtracking is this way to solve constraint satisfaction problems. It works like it sounds. You keep trying to advance the solution, and then when you run into a problem, you backtrack to a previous solution that doesn't have any problems and try to extend it a different way. You keep backtracking anytime you run into an issue, and then you hopefully find a way to solve the problem in the end. It's useful for solving the type of algorithm problems known as constraint satisfaction problems, where we're trying to figure out, can we do what we need to do without violating all of the constraints that we're given? If it's possible, often we need a specific solution. Sometimes it's as simple as just knowing that it can be done is good enough, right? But if we need a specific solution, we can use this type of algorithm to find one. And some of them may have more than one solution depending on the constraint satisfaction problem. Some constraint satisfaction problems have a unique solution. The examples that we used previously were sorting. Sorting is a constraint satisfaction because we know that the constraint holds that every item is not less than, is not less than the items that follows it, right? Sorry, I said that right. That's good, yeah. So that's what we have a sort when we think of sorting, and remember we said that sorting means sort increasing. So if every item is not less than the item that's in front of it, then we've got something that we can consider sorted. Puzzles, things like number puzzles, Latin squares, Sudoku, all kind of puzzles. I'm nonstop with those things on my phone. That's what I do. I play number puzzles. It relaxes my mind. I can think. There's a GRE section back when we took the GRE. I don't know if that's going to be reinstated post-COVID, but that's the thing. There was the analytical section. You're solving constraint satisfaction problems. And you've seen these before where you're trying to figure out there's 3 houses. Each one has a particular color. Each one has a particular owner. And then you have a question and say, well, the red house is to the right of the house owned by Sheila. And then you try to figure out who owns which house and which color is. That's the type of constraint satisfaction problem that you can solve with backtracking. You say, well, the red house is owned by Tommy, and then you go forward until you find that that violates something. You have to back up to say, well, maybe when I said that Tommy owned the red house, I needed to pick somebody else. And then I picked Greg, and now when Greg owns the red house, I can try to extend the solution farther forward. So these are constraint satisfaction problems, and that's a sort of an outline as to how we sort of look at backtracking a constraint satisfaction problem. We do, in theory, go over all possible solutions. So asymptotically, this looks like brute force because we're looking at everything. As we take a particular input combination, this is one of the things I think, and I set that one there and that one there. Does that satisfy all the constraints? If it does, then I've got a solution. I can oftentimes stop when I've found one solution. As I mentioned, some of these problems have only a unique solution, but usually if there's multiple solutions, the goal is to find out whether a solution is available and whether we can find one that we can implement. So oftentimes we can stop as soon as we've found one. This piece of text down here says that for particular problems, for any particular problem that we're trying to solve, there may be a much more efficient approach, but using a backtracking algorithm is a fallback for solving the constraint satisfaction problem, in the sense that if I don't have a really efficient algorithm, there's something between pure elegance and brute force. Brute force on the low end, which is where I've got to do more work than I can imagine, or all the work that's possible. So I've got pure elegance over here and brute force over there. Backtracking will usually fall somewhere nicely in the middle. So if we can't get some really nice algorithm to get this done, we can always write a backtracking solution that does get it done and usually ends up much better than brute force. Here's the general form of backtracking. And it's got some building blocks in it. We will move those building blocks around as necessary for different versions of backtracking solutions, but they will all have those same building blocks. This particular version is called check node because we're checking a node for giving it some assignment, setting some input to a particular object or state. So check node is this function, and we see the last line of it here is a call to check node. So this is a recursive function. Check node calls check node. We can't have a recursive function without a base case. We need some way to exit without recursing. And this base case doesn't look like a lot of our base cases in the past, but we see that the if promising here encapsulates the call to check node. So if promising, excuse me, if the promising call fails, then we exit check node without calling check node. End of recursion. So this is a base case. If we've got something that terminates our recursion, then we have no problem trying to go forward with recursion. This check here, if promising V, says, let's see what the current partial solution looks like. And this V is given in particular because we think of the solution as being built up one node at a time, one part of the state at a time. So if I'm doing a Sudoku, I've just put in one digit in a particular square. That's something I can now check to see, well, was that a promising placement? If it is, I try to put another digit in another square. And if that's promising, I continue working forward. So each one of these nodes, this is what check node is all about. As we check this, we're checking it to see, is the most recent placement a good one? And it doesn't mean we can't check all of the previous placements. In many instances, we do have to check all of the previous placements just to be sure that this current placement hasn't violated any constraints. But this is called with the currently advanced solution. This is the farthest we've advanced it at this under this current branch. So if it's promising, then we've got to say, well, that was a good thing that I did. And then there's two options. Once I've done something good, the two options are, well, it's the last thing that needed to be done, so I'm out. That's what this first if is inside the if. If that thing was promising and it's a solution, we're done. In this case, we're going to write the solution or do whatever you need to do with the solution. We can sometimes exit here depending on what we need to do if we only needed one. However, if we continue on, this will continue to recurse, right? So if we've got a solution because this is promising, that's one outcome. The other outcome is, well, it's promising, but it's partial. So in order for us to get a full solution, we need to extend the solution. And that's what happens in this else down here. It goes through iteration. And so we've usually wrapped a loop around our recursion because that loop needs to go through all of the options for a particular node. So in this case, we're looking at for each node adjacent to V. This is how many ways can I extend the solution at V. I was called with this version of V. I said putting something in that particular node is promising. So then let's see what we can do to move past that. And normally there's a number of choices there. For instance, when we were talking about graph coloring, after I've colored one state and I move to the next state, I have to run through all my available colors with this for loop to check all of the nodes adjacent to it in this particular explanation. So as I have some set of choices to apply to every node, I'm going to use this for loop some sort of iteration to get me through all of those choices. And every time I choose one of those things, I'm going to try to advance my solution by moving forward with that choice. And that's where the recursive call to check node comes in. All right, this is an alternate form of backtracking. We see now that the building blocks are there. I've got a call to solution. I've got a call to promising. I've got a recursive call to check node. It's wrapped inside of iteration here with a loop. But they've kind of moved around, and logically that still works. So if you understand what's happening here, I've got some node that I'm advancing as something good. Right? So the first thing I want to do is be able to get out of this recursive function, right? The check node, if there's a way for me to avoid calling check node, then I say I've got a base case for this recursion. And the base case is, hey, look, I've got a solution. Great, I don't need to extend the solution. Remember, the recursive call to check node is a way to advance the solution. So if I've already got a solution, I no longer need to advance it. So that's what's up here in this first if. If I've got a solution, if this V that you've just given me is a solution, then we're possibly done. Write that solution or store it or do whatever you want to do once you've found a solution. Silence. So if solution, write solution. So there's my check. If V was a solution, I'm okay. Otherwise, I know that it is not a solution, but it's a partial solution that I may think of advancing. Say, well, wait a minute. How do you know that it was even promising? Well, we've moved this promising call on this version inside the for loop. So here I'm going to check each one of those options, and before I even move forward, I'm going to say, is this promising? And if you think about the previous slide, it did the same thing. It said, well, if this is promising, I'll try to extend the solution. So this has kind of pulled those two portions a little bit closer together, but effectively it works the same way. I'm going to run through this loop trying all of my options. For each option that is promising, I'm going to try to extend the solution. Then when I extend the solution, the first thing I'm trying to see is, well, if it's promising and it's new, is it actually a complete solution? If it is, then I write it. And so the same things all happen. It's just like looking at things that I could do in a loop, maybe steps 1, steps 2, step 3. I can get the same work done if I go step 3, step 1, step 2, or step 2, step 3, step 1. It's just kind of a little scrambling of it there, but everything that we needed to get done happens in an order that does make sense. As we have this general form of backtracking, we've called it check node, but you may call it whatever you like. We've got this function that's called solution, and this is a pseudocode function. It doesn't necessarily have to be a function, but it does have to be a way of checking to see whether or not the depth of the solution is as deep as I need it to be. This is often very simple. For instance, if I'm doing map coloring, the question is, there's 50 states. Is this state number 50? If so, that's a solution, right? If this is state number 42, we still got some states to go. This is not a solution. Same thing works with the Sudoku, for instance. We've got to fill in 9x9 grid with digits 1 through 9. If I don't have 81 digits on the board, it's not a solution. As soon as I put that 81st digit up there, solution becomes true. So oftentimes solution is a really simple thing to check. It's not usually the problem. We're checking what's called the depth of the solution because we're looking at this as sort of a depth first search. We're saying, hey, can I get all the way down to the bottom before I do that? So what that in terms means is, can I get to all 81 digits here before I start judging other values moving across the decision tree? So I've made one decision at this first node, and I make another decision below that. There's 9 decisions below that because I'm filling in the next one, and so on and so on and so on. If I'm looking at my graph coloring, I've got this first state. I can color one of 4 colors. Below that, each one of these things has another state, which I might color 4 other colors, and each one of those has something below it. And so this is the depth of my solution. When I get down to having colored all the states, I have a solution. Promising, this is where the work is done in backtracking. This is the one that's often a lot more difficult to figure out. How do I know that this partial solution hasn't violated any constraints? That's where the checking needs to come in. And most problems have their unique way to get this done, but that's why it says it's different here for each application. But the goal is to see, hey, I've got some partial solution. Has it violated any constraints? And then check node, of course, is the function that we're working in itself. This is the recursive function. It gets called only if we have a partial solution that's both promising and not a full solution. And so you can see that we can order those two checks in different ways. I say, well, check node will be called if it's a partial solution that's promising and it's not a solution. Or I can say check node will be called if it's a partial solution that's not a solution and is promising. And that's how we get those two alternate forms that we looked at. We just kind of reordered those two things in the and. Really, they both need to apply, and if you do one before the other, you still end up with the proper answer. So here's our specific example. It's a problem called n queens. And the premise is to take a chessboard and place the number of queens in there equal to the number of squares on a side. So we'll start out really simply. If I've got a 1x1 chessboard, can I place a single queen on that board so that that queen is not threatened by any other queens? And this is trivially easy because there's only one queen. But as I'm working on this, I see, well, how does a queen work? Queens in chess have infinite move ability. I suppose they're limited to a movement of 8 in typical chess because the board is limited to a size of 8. But queens can move unlimited horizontally, vertically, or diagonally as long as they go in one direction during a move. So they are really a really dangerous piece because they aren't constrained much at all by distance or direction. So that's what comes as the part of this puzzle is how can I place a bunch of these queens on the board? Now this is not a legal game of chess. If I've got a normal chessboard that's 8x8, the goal is to place 8 queens on the board in such a way that none of them is horizontally adjacent, none of them is vertically adjacent, and none of them is diagonally adjacent to any of the other queens. Really simple with a board of size 1. Now with a board of size 2, it's impossible. We've got 4 areas that 2 queens can be in, and each of those 4 areas is either horizontally, vertically, or diagonally adjacent to any place that I can put the other queen. So with 2 queens, it's not possible. 3 queens is similarly difficult, right? With a 3x3 board, trying to place 3 queens on there that can move all the way across, all the way down, or all the way diagonally, there's no way to do it without threat. However, at n equal 4, now we've got a chance. We can put 4 queens on a board that's 4x4 in such a way that they do not threaten each other. I'll give you about 5 seconds to figure that one out. That's not very fair. But it does give me some water. We're going to show you how to do it. That's the trick. But I thought you intrepid explorers might want to get after trying to figure out how to do a 4x4 n queens. After 4, I believe it goes on to infinity. I don't know that this has been proved to be accessible for everything after 4, but I don't know of any numbers above 4 that has been proved that you cannot find a solution for. So it goes on and on. Let's go back and look at this. The way that we're talking about placing these queens on the board, each queen can move horizontally, vertically, or diagonally as far as they want. If I was going to try to solve 8 queens, I've got a standard chessboard, and maybe while you're practicing this, you use a bunch of pawns. They all look the same. You can imagine they're queens if you squint. Brute force tries to put those 8 queens in a whole lot of places. It turns out there's 1.785 times 10 to the 14th different possibilities for placing 8 queens on an 8x8 board. And many of these are ridiculous board configurations, like all 8 queens on the same row. Of course, they all threaten each other. It's not just one threatening another, it's all 8 of them threatening each other. So that's ridiculous, but you know, brute force. Brute force doesn't care about ridicule. Brute force gets it done. So brute force would find it, but it would spend a lot of time. If we apply backtracking to this, this is still has the same asymptotic complexity as brute force, but if we put a little bit of sense into it and some backtracking, in our sensible version of it, I say, well, if I'm going to place 8 queens, and I know that they can go as far as they want horizontally, and as far as they want vertically, and as far as they want diagonally, maybe I'll place the 8 queens, but I'll only for sure place 1 in every row. That's already managed one of my 3 constraints, because I say I know I'm never going to place one in a row that already has a queen, so now all I have to do is check columns and check diagonals. That's sensible. That takes this really large brute force number up here, 1.785 times 10 to the 14th, and knocks it down to something like 16.77 million. Now that's huge. That's 1.6 times 10 to the 6th, 1.6 times 10 to the 7th versus 1.7 times 10 to the 14th. Huge improvement. It turns out that there's 92 different ways that I can solve the 8 queens problem, and this would find it by looking at those 16 million possibilities. How do we further reduce this search space? Oh, what has happened to my beautiful slide? Don't do it, don't do it. I don't know what's going on here. It should look better than it does. Hold on, let's see if I can't recover here. I do not know what happened to that. It wasn't me. I know that for a fact. Here we go. H281 lecture slides. Yeah, it grew and sucked up the water from all the other ones around it. Lec 22. And that was slide 12. Hopefully the slide gremlins didn't get me on this one. Yeah, this is more what I'm talking about here. Okie dokie. Let me get this window sized properly. And closing this one up. Don't save. PowerPoint. Hey, wait. All right, now that's what the slide is supposed to look like. This is an example of 4 queens. So we've got this 4x4 board, and my first step is I'm going to start by sticking a queen in each one of these rows. I'll try to figure out a good place to put it. So a nice place to start in the first row was in the first column. So we start there, put a queen down. As we, come back to me here. There we go. As we move across, I see that trying to place a queen in the second row, in the first or second column, instantly causes a problem because they're under threat by the queen in the first row. So we'll place one in the third row, third column, second row. And we have no problems because there's no threats available. Then I move down to the third row. Third row, first column is threatened by the first queen, and then the second, third, and fourth columns in the third row are all threatened by the second queen. So this is a time to say, well, as I try to place this, it fails, I backtrack, I try another thing. The second column fails, I backtrack, try another thing. The third column fails, try another thing. The fourth column fails, and there's nothing else I can try in this third row, so I have to backtrack even farther, which means let's go back to the most recent decision, the most recent successful decision that I made, and update it. So I'm going to change this queen in the second row, is what my backtracking here does. So I backtrack to row 2 and say, let's move this queen from column 3 of row 2 to column 4 of row 2. Once again, things are looking good. I've got no threats with those two, so I can start on this third row again. First column is threatened by that queen in the first row. The second column is actually pretty clear. And I got this, this one needs to be reordered a little bit. But this second column is available. So as I put one there, I see that now I've got 3 queens on the board in row 1, column 1, row 2, column 4, row 3, column 2. No threats anywhere yet, but as I try to place something in the fourth row, we see that all 4 of those locations, once again, are singly or multiply threatened by the 3 queens that are there. but there's nothing clean that I can put in there. If I try to backtrack in the 4th row, I find that none of those work. I go to the 3rd row, and we've already seen that nothing else in the 3rd row works. And I go backtrack again to the 2nd row. I say, well, the 2nd row is done. We've tried everything in the 2nd row. Let's backtrack even further to the 1st row. Maybe that first decision that we made was one that made it impossible for us to come up with a solution. So we do end up backtracking, in this case, all the way back to the queen in the 1st row. We'll show you that in just a minute. I know you're on the edge of your seat. So, as we said, constraint satisfaction could require one solution. The version that we have is going to go through multiple solutions. It could require several, or it could require all of them. That's up to the current problem specification. But as we look at n queens, remember those things that we had, those building blocks of backtracking. We had promising, we had solution, and of course the check node function itself. So solution is pretty easy. As we're placing n queens, if I haven't placed the nth one, then I am not done. So in this 4 queen situation here, if my solution is node 2, I'm not done yet. If my solution is node 4, this is 1 indexed, if my solution is node 4, then I'm done, right? If the node that I'm passing to solution is node 4, because this is a promising way to place node 4, or row 4, the queen in row 4. If I found a promising way to place the queen in row 4, then I've got a solution because I haven't violated any constraints and all 4 of them are done. Really simple solution call. Check node, of course, is pretty easy. We're going to do that recursive thing. We call all positions of a particular column. So that's what our goal of advancing the solution is. As I'm moving to this new row, the for loop, the iteration portion of this has to say, well, let's try this column, this column, this column, this column, this column, and then when we move on to the next row, we start over and do all of those columns again. So the recursion calls check node, and then the iteration is checking each one of the new columns in a given row. Here's promising. Promising is fun. Promising is fun for every one of these problems because that's where you really get to do the art of programming. The rest of this is a bit structural. But here in promising row col, what I'm looking at is, can I place a queen at this particular row and column? We'll see how this one all gets pulled together, but that function is, can I place a queen in this row or column? And you might think of, well, if I stored this as a 2D thing, I look up the rows, I look up the columns, but how do I get that diagonal thing? That's a little bit complicated. It turns out thinking of this in a 2D way is a lot more complicated than it's worth. So here's this really unique situation, unique solution that's kind of elegant, right? So instead of thinking of this board as a 2D thing, as I'm trying to figure out whether I'm promising or not, I'm going to break this down into some vectors, 1D vectors. And what I'm going to do is say I know that the row is good because I'm the one that's controlling which row things go into. Then I've got this collection of columns that tells me if a particular column is available, meaning some queen is not already on this column. And I can do that just as bools. Then I've got these other 2 1D vectors here that are another couple of bools, and they say, is that left diagonal you're trying to place in row col available, as no other thing is on that same diagonal as the incoming row col. And the same thing here for right diagonal does it, right? And then the last thing that I need is one more vector that holds my position in each row, right? And that one is a vector of integers, but there's just n of those. So I've got this n size vector of available columns, this n size placement of rows, and then we'll figure out the size of these left and right diagonal. But they're all one-dimensional, and it allows me to check whether or not a position is available in constant time, which is great. Summary of 4 queens, right? We talked about the 8 queens having the 16,772,000 different leaves. That means those are the ways that I can place these things. When I simplify this to 4 queens, the entire tree boils down to having 256 leaves. How is that? Well, we've got 4 choices at the first level, times 4 choices at the second level, times 4 choices at the third level. If you're with me, that's 64. Then I multiply by 4 more to get to the bottom level. Those are my leaf nodes. Those are the 256 ways that I can place these 4 queens with only 1 in each row. The backtracking algorithm that we're looking at is going to allow us to search just 19 of those 256 branches before we find the first solution. So if you're keeping track, that's fast. it's better than 256 if we're looking at that as the brute force version of it. 19 is pretty nice, and then it only gets much better as we get into larger and larger values of n. Promising, remember, may lead to a solution. Not promising will never lead to a solution, so we can prune that. And once we've pruned it, I know I can't put 2 queens in the first 2 columns. I never have to figure out what's below that, because if I'm looking at an 8 queens board, remember, at every level there's sort of factorial work remaining. So there's 8 factorial things I can put up there when I've got 8 of them. There's 7 factorial after I've put 1. After I've put 2, there's 6 factorial work to go. But if I know that these 2 are invalid, I can save that 6 factorial work, and it's pretty impressive. Here's how we calculate those 19 branches. So I've got this small 4x4 chessboard here, and we've labeled each one of the locations with a single character because it makes it easy to look at them. A, B, C, D across the top 4, E, F, G, H, second 4, I, J, K, L, third row, M, N, O, P, that's the 4th row. So as we look at searching these branches, I start out by placing a queen at A. That's my first branch searched. As I go to E, I find a vertical threat. That's me trying to put something in the 2nd row, 1st column. There's 1 branch investigated. So now if I move over and say A to F, well, this is 2nd row, 2nd column being threatened by 1st row, 1st column because it's a diagonal threat. So I'll try something new. How about A to G? That looks good. I have no threat here. We saw this in our previous investigation of 4 queens. So then I try A, G, I, which is placing something in the 1st row, 1st column, 2nd row, 3rd column, 3rd row, 1st column, and that's of course threatened by that 1st queen. So I say that vertical threat prevents me from going there. As I move over to AGJ, that diagonal threat prevents me from going there. I move to AGK, there's 2 threats. It's diagonally threatened by the 1st row and vertically threatened by the 2nd row. So I move on to the 4th column in the 3rd row. It's threatened, of course, by the queen in the 2nd row. So there's my 6th branch investigated. So far, no bueno. Time to backtrack. I do that by moving my 2nd row over to H. So now I'm looking at an AH, which looks good until I try to place something in the 3rd row. AHI gives me that 1st column threat again. So I'm going to move on by changing to I. So far, I've got some options after H. I'm going to try all 4 of them. This is my for loop trying to advance my solution to the 3rd queen placement. AHJ, that looks good. I've got no threats here. This is where I tried to advance my solution to the 4th row previously. But when I push something in the 1st column, we saw that AHJM gives us threat, AHJN gives us threat, JO, there's threats all abound there. So that 4th row is no good. I'm going to backtrack to the 3rd row, try something new after AH. How about AHK? Well, there's 2 threats on that. AHL has a vertical threat. So now I've tried everything in the 3rd row with this first 1 and 2 row combinations. But if you see, if I backtrack to the row before that, I've tried everything in the 2nd row as well. So as I backtrack finally to the 1st row, I'm going to update that 1st row to be B. Okay, well, 1 queen placed, no threats, we're good. Moving on, I've got a diagonal threat there, BE, vertical threat BF, diagonal threat BG, but BH, that looks good. I can try to extend the solution. This is how you say promising, right? Because B doesn't threaten H doesn't threaten B, and I'm ready to go in row 3. I place something in that 1st column now. Since that 1st queen is not on the 1st column, this is actually a doable thing. I've got no threats on I, so BHI is a good start. BHIM, however, gives me vertical threat. I'm gonna backtrack and change that to BHIN. Now I see this one is really busy. There's 3 threats on this. All 3 of those queens can hit BHIN. So I'll move to BHIO. And this gives me my first solution after investigating my 19th branch. And so this is what I say when there's 256 ways I could have done this by placing the queen in these first 4 positions, followed by any of those 4, followed by any of those 4, followed by any of those 4. I could have done 256 different versions of it, but just after 19 of them, I found my first solution. That's pretty cool. That's backtracking. So if I look at what I call this search tree, I'm talking about getting down to this depth, right? So with n equal to 4, I'm trying to figure out, hey, I can put a queen 1 in either column 1, column 2, column 3, or column 4. This is what my decision tree looks like. After I've decided, say, column 1, I've got the I've got to try to place queen 2. That's the second row, and I've got 4 options there: column 1, column 2, column 3, column 4. What we saw was that each one of these gives me those 4 choices. So here's where I've got 16 ways that I can place a queen 1 and a queen 2. And that's pick one of these first ones and then pick one of the 4 below that. All right? Well, I do have a threat here, right? If I've got 2 queens in the first column, that is not good. That's something that I need to prune. I'm going to prune that. And what does that save me? It saves me all 4 of the choices of queen 3 below there. That's great, because I can do this. It saves me when I don't have to do the 4 choices in row 3. I don't have to do the 4 choices in row 4 below that. So there's 16 things that get pruned out of my ultimate 256 just by saying this first 2 in the first column give me a problem. So I get those savings kind of like all over the place, because I go to column 2 for queen 1 and column 2 for queen 2. There's another 16 below that I don't have to check. Column 3 for queen 1, column 3 for queen 2. There's 16 below that I don't have to check. Column 4 for queen 1, column 4 for queen 2. 16 more that I don't have to check. So just after placing those 2 rows, I've pruned off 4 sets of 16. I've pruned off 64 final states just by checking those 2 rows in a what we call responsible manner, right? A sensible way to place those 2 things. So now I've pruned 64 of those bottom leaves. That's 25% of my search space completely pruned after just 2 placements. And that's where we get some really good speed here. We see our ultimate solution, remember, kind of broke in off there in the middle there. There's 64 branches here that I'm looking at across this 3rd row. With these 64 branches, I'm trying to figure out how many of them do I not have to deal with. As I get down to the rows below that, I see that there's 256 leaves, I should say. That's me placing all 4 of the queens, 1, 2, 3, and 4. And this one gives me actually a mirror image of the solution that we previously saw. Let's see if we can find it in there. There's one in column 3 in row 1. There's one in column 1 in row 2. There's one in column 4 in row 3. And one in column 2 of row 4. That is actually another solution for 4 queens. All right, so our summary on backtracking. It allows this pruning of branches that are not promising. All my backtracking algorithm have some similar building blocks, and there's some pretty decent form that you can set up reasonably with a backtracking algorithm as well. So if you know you're trying to solve some problem with backtracking, you can put a backtracking skeleton up there, then try to figure out, well, how do I consider I've got a solution? Got that figured out. How do I consider that this is promising or not? Got that figured out. How do I try to extend the solution? And then your solution just works. So backtracking can be easily written. The problem, or the challenge, I should say, usually is just trying to write promising. Because that's the one that's got to check all the constraints and make sure that everything that's been submitted isn't a violation. That's backtracking. It helps us solve constraint satisfaction problems. It is a fallback. It is like well, in the worst case, I can do a linear search, right? It's better than having to do brute force. So that's what backtracking is. Up next, we'll look at branch and bound. That's what is going to get you through Project 4, Part 3. So if you are currently asleep, please wake up. It's time to go to work. All right, we've seen this slide multiple times before. We've grayed out the part that we don't even care about now. We're only worried about optimization problems, and optimization problems have at their base a constraint satisfaction problem, because there's no sense optimizing some solution that just doesn't work. So we have to satisfy all the constraints. Then we add this objective function that says, hey, well, here's a solution. Is it a better solution than this other solution? We use that objective function to compare solutions. See which one of them is better. So in optimization problems, we're going to need to compute this objective function more often, right? So we say, well, I've solved this. Now let's call the objective function to see if this solution is worthwhile. I can't stop early because I never know when the next solution I find might be better than all the solutions I've seen so far. So we end up doing a bit more searching into the space here, but luckily, just as the fact that it's, harboring a backtracking solution underneath its hood, this is still no worse than backtracking. So that's to be saying that's no worse than brute force. Wow, congratulations. So as optimization problems solutions goes, we know this is never going to be asymptotically worse than brute force, but we saw how backtracking gave us quite a bit of savings, and the way that we're going to apply branch and bound is going to give us even more savings. Once again, it won't change the asymptotic complexity of it, but it does end up making things be a lot faster than brute force. Optimization problems, of course, are a fallback. So we can have a more efficient, more elegant solution for a particular problem, but if we can't figure out that level of elegance, we can always just write branch and bound. We'll call branch and bound B and B. It's the idea of backtracking, really, because I mentioned it's in there, and we extend it to optimization. So we're trying to use this to minimize some function with a useful property. So what this means is, as I've got some partial solution now, when we were concerned with backtracking, we were only concerned without to make sure we could do this without violating any constraints. What branch and bound does, it adds this ability to say, well, I'm going to estimate the remaining work to be done. And this, if you're wondering how that gets done, that's the new challenge. We talked about promising being the old challenge. Promising still exists, and now we've got this estimation thing that is another portion of it that has to be done. But what we do is we say, well, I've got a partial solution, and it looks like, because of my estimate, there's about this much more work to be done. Well, if I'm doing just a constraint satisfaction problem, that amount of work to be done doesn't make any sense. When I'm doing optimization, though, I say, well, when I'm optimizing this, I'm trying to find some shortest path. I'm trying to find some maximum amount of value I can encompass or something. I'm trying to take something and optimize it. I'm trying to maximize something or minimize something depending on what the problem is. So as I look at partial work to be done, I realize there's some more work to be done. So if I've placed 2 suitcases in the trunk, for instance, and I got another pile of suitcases to go, that's a partial solution. And look at the amount of work to be done. Is that going to make me successful, right? And so I've got the violations of constraints that I have to worry about. But now, since I'm trying to optimize, I can say, well, once I've come up with a single solution, I say, well, anything that doesn't improve upon that solution is also a waste of time. So if I've got a partial solution that looks like it's going to take more time than that, even though it hasn't violated any constraints, I can prune it. Even if it's just as slow as that, it doesn't even have to be slower than. If it's not faster than my current best, I still prune it because it doesn't represent improvement. So that's what's good. So I add this new constraint, which is, hey, we're optimizing. I have all the other rules that I have to follow, but then it looks like if this one isn't giving me an improvement, I'm going to prune it anyways. No violations, still done with it. It's taken too long. So here's our general form. This hopefully will look fairly similar, and that means you weren't asleep moments ago. I've got a promising call there. I've got a solution check there. I've got a call to check node there. Woo! That's backtracking. I told you it was hidden in there. But I've got this recursive call check node, calling check node. All of these things that was good before. And I've got this base case that says if I fail the promising test, then don't even try to extend it with check node, and so on and so on and so on. All right. So here with check node, I've got now this current best. And this is important because now I need to be able to check the problem solution so far along with the constraints to see if I violated anything. But I also need to know, well, this is a partial solution. Am I going to be able to beat the best that I have so far? And if I don't know what the best is, I can't check that. So this check node has been augmented from backtracking to also include whatever it takes me to keep track of current best. And one way to do this, of course, is to keep passing this. But a better way to probably pull that off is to stick this into a class and then have access to some member variables, because we are calling check node from within check node. And so everything that you put into the stack frame, which is parameters, increases the size of your stack because you're going recursive there. So we can put those things into a member variable and we still have access to them. That works just as well. But what we've got here is if promising, and promising looks about the same as it did before, but it also includes that current best, because we need now, that's where we actually need current best to say, well, this is promising because it hasn't violated any constraints, but it's not promising because it's too expensive. So we're not doing that. So we have to pass current best on to promising. The solution check is similar. Now we've got this update of current best. What does that mean? The update of current best means if I've got a solution, then I may have found a better solution, right? And this promising says it's a better solution than what I've had so far, otherwise it's not promising. So if it's a solution, I need to update my current best because it is a full solution and it's better than I've ever seen. So that update of current best means you've got to copy this if you need it. Or maybe if you just need the total cost, you need to copy that total value. So it depends on what you're called on in the project. If you need to just have the cost of the thing, that's good. If you need to print out the actual thing, then you need to copy it here as well. That's what this update function is, and it's going to vary from problem to problem. The rest of this is something that we've seen before. We've got this iteration here to wrap all of the choices, and then I've got a call to check node, which of course has to forward on current best if we've called it up there as the way it is. And in the end, we get done where we're going to return current best here, and that gets us out of this particular version, right? So this is one way to look at branch and bound. What's new about it? Solution is similar, update is new, and this is what I mentioned here. If the solution is better than the current solution, then I'm going to update this. This is my optimization step because I've seen something better than I've ever seen. That's the one I want to keep track of. Check node is similar as before. And then now we've added something here that we haven't seen just yet. This is this lower bound. And this is where the bound of branch and bound comes from. One of the bounds anyways. So this lower bound is what I alluded to when I said we've got some estimate. We've got to do some estimate. So when we've got a partial solution, that's not something that I have to estimate. So if I'm trying to find a way to optimize a path length, for instance, and that means me jumping from node to node to node to node to node to node to node. If I've got some partial path, I've got these first three nodes already picked out. I can completely measure the distance between node A to node B to node C, add that up. That is not an estimate. But when I'm trying to figure out, well, how much is it going to cost me to get from C to G? Well, that's where I have to estimate. So I'll say I've got the cost so far, plus I've got this estimate of what remains. And it's important that this is an underestimate, right? So I can be wrong with that estimate. But what I don't want to be is wrong and too long. I want to be wrong and too short. Wrong and too short. Why? Because if I'm wrong and too short, that means I'm wrong and I'm saying that's not going to cost as much as it actually does cost. But if it looks like it's going to be cheaper than it is, I might try it. Right? I might try it. So if you're trying to find a nice way home, you say, well, I've got one way home that takes me 50 miles. Right? I'm gonna try this new version of it, and I go down this new highway, and it looks like I'm about a third of the way home, and I've already gone 10 miles. That's not too bad. So what's remaining? If I think what remains is another 60 miles of work, I'm not going to go this way because the 10 miles that I've already gone plus 60 more gives me 70, and that's not better than my current best, which is 50. So I say, well, that 10-mile trek is a bad start. So that's what happens when my estimate tells me to leave. Now, if my estimate is right, like perfect, and it is 60 miles, and then the 10 plus 60 is 70, then I still don't want to go that way. If my estimate is wrong, but it's short, so the estimate says it's 60, but it's really 90, then 10 plus 90 is even worse than 10 plus 60, and I still don't want to go that way because it's not better than 50. Now, if my estimate is wrong, however, and it's wrong long, So I think it's 60, but it's really only 30. I say, well, this 10 plus 60 looks bad, I'm not going to try it. In reality, it's only 30. 10 plus 30 would have got me there cheaper than the 50. So then my estimate, if it's too long, it will prune something that I don't want pruned. It will say, that looks like a bad idea, don't try it, even though the optimal solution may lie along that path. So it's important that this lower bound be this combination of what I actually have spent so far plus some underestimate of what remains. If it's an overestimate, then I will probably prune the best solution. Promising here is now different. It's of course different as it always has been. We have to do the constraint violation thing. But I also have to say promising is going to return true when this lower bound estimate is less than my current best. If the lower bound estimate, which is the combination of what I've got on my partial path plus the underestimate of what I haven't pathed so far, if I've got that, then that's promising. If promising returns false, of course, that's what gets me pruning. And that pruning comes from either violating a constraint or just being too expensive. The key to branch and bound is the bound. The efficiency of B&B is, of course, based on cutting things away, pruning things, getting rid of unpromising partial solution. And we saw earlier that the earlier we know a solution isn't promising, the more I prune, so the less time I spend investigating something that isn't going to work for me. So the more accurately I can compute my partial costs, the earlier I can prune. Remember, it's okay for me to be inaccurate as long as I'm not inaccurate long. But what happens then if I'm inaccurate short, like too short, way too short? Say, oh yeah, that one looks good, that one looks good, that one looks good. Oh, my estimator is just, it's always short because I don't want to go over. Well, if it's too short, then everything looks good and you haven't really saved yourself anything from bounding. You're just at backtracking. We're trying to get some optimization. We're going to get some speed out of this. And so the more accurately I can compute those estimates, the more I can prune. And oftentimes we'll see that it's worth spending extra effort to compute these bounds. And what that means is a lot of algorithms that we might have been scared to touch here in the first 3 projects. We were so concerned about getting this done and having the best possible algorithm and so much speed we needed. But if, as you're working on project 4, you're encountering this algorithm that is factorial. Factorial is intense. Say, well, I'll take something that's quadratic. I would even take something cubic if it prevented me from doing something factorial. So that's what it says here. Sometimes it's worth spending a little extra effort. It's okay to do something that's n squared. If it's keeping me from doing something n factorial, it's even okay to do n squared log n if it keeps me from doing factorial. But in project 4, I want you to stick to n squared. But as I'm saying here, it's okay to do that extra work if it saves me more time later. We're going to be working on minimizing with branch and bound in project 4. The traveling salesperson problem is a minimization problem. How can you get from start all the way back to where you started after visiting all of these locations and do it with the shortest path possible? So this is a minimization. One way to do any minimization, whether it's this or even just to find the smallest item in the loop in this container, is you start with the largest possible item. You start with some infinity, and then everything that you see that's shorter than that is good. So one way to do it is start with an infinity bound. Another way to do it is to find some complete solution, any complete solution, and then use its cost as the upper bound. So I either start with infinity or some partial or some complete solution that says, well, here's a solution that anything that's longer than this, I throw away. Obviously, nothing is longer than infinity, so infinity is open for all business. But any first solution I find can say, if it's longer than this, well, I can throw that away. And then as soon as I've got some partial solution and a calculation of the lower bound estimate, then I can say, well, if that's better than my complete solution, then I'll keep going. I'll keep trying to extend the solution all the way till it's a complete solution. If it's not better, then I prune it. I prune the partial solution when the lower bound exceeds the current upper bound. And the upper bound is my current best so far. Remember, we said when we got a first complete solution, we use that as an upper bound. So we've got 2 bounds. We've got an upper bound and a lower bound. So our upper bound is a solution. Every time I find a better solution, I lower this upper bound, I lower this upper bound, and that upper bound means I'm not willing to do any more work than this because I already have one that's this good. If I go above that, that's a waste of time. And so every time I find a new solution that's better, I lower my upper bound, and that lowers my search space, and I can't search above that because it's a waste of time. So I've got this upper bound that keeps lowering every time I find a solution that improves things. In the end, the upper bound is the answer, because that's the best thing I've seen so far. And then the lower bound, so I've got an upper bound and a lower bound. The lower bound estimates how much work I have for my partial solution to the end of the solution. If my lower bound sticks below the upper bound, then I've got something. But if I've got this much partial work and then my lower bound says you're gonna go up there to finish, then that seems like it's a bad start. So if my new complete solution gives me a lower cost, that becomes the new upper bound. When I finish, the upper bound is my answer. Here's just a slide that I don't want to confuse you with too much, but it's important to recognize that you can use branch and bound to maximize. This is a minimization project, project 4, but if you have to do a maximization, all you have to do is turn everything on the previous slide around. Instead of starting with an infinity bound, you start with a 0 bound. Anything's got to be better than 0, and the next thing that I see that's better than that, I keep that. So as I find my first complete solution, I'm using that, and since I'm doing a reversal here, minimization to maximization, my best answer in the end is now a lower bound, and my partial solution is an upper bound, and so on. So this slide just kind of goes over the reversal of that. Like I said, don't get too confused into this right now. It's going to be hard enough to deal with minimization with BNB on your first time out. Later on, if you need to do a maximization, this set of bullets here, these 6 bullets, say exactly what we need to do. All we do is reverse everything. We're looking for our estimates. Now, our estimates have to be an upper bound estimate, whereas previously we had to have a lower bound estimate, and so on and so on. Here's my branch and bound summary. We use this method to prune a search space for optimizations, right? We keep track of our current best solution, and then anything that improves upon that, we use that to extend, to do more pruning here. And we do this partial solution, and I combine that with an optimistic estimate. Remember, I need to be optimistic as if I would like to try this. So if I'm wrong, I'm pessimistic, it's like, oh, that looks like it's way too far, I won't even try it. That's not good. You say, well, optimistically, that might work, so I might try this. And remember, though, the more optimistic you are, the more you end up trying, the longer you end up taking. So when you want to be optimistic, remember, we want to be on the good side of the answer, but as close as we can get to that answer, the quicker we're going to be done with this search. All right? If an estimate is not an improvement, right? Remember, because this estimate is optimistic, if the estimate is not an improvement and reality is worse than the estimate, then the actual is not going to be an improvement either. So if my estimate is not an improvement, that's what allows me to prune. All right, that is branch and bound. Having a look here at the TSP, the traveling salesperson problem, let's go into this just a little bit. This is the TSP defined. It is a Hamiltonian cycle here that we're going to be looking at. And a Hamiltonian cycle is given some graph G with vertices V and edges E. Find a cycle, that means you start at one location and end up at that location. Find a cycle that traverses the node, every node in the graph, exactly once. So we have to go to every location. And this is where the traveling salesperson thing comes in. We want to go sell at as many cities as we need to without revisiting a city, because when you revisit a city, you're not going to make sales there. If you didn't make them the first time, you aren't going to make them the second time. So no vertex can appear in this list twice except the home base, because you want to leave home, sell, come back home, go to bed. That's great. That's a constraint satisfaction problem. Is there a way for me to do it? Can I even make it because of the roads that are available and because of the locations I'm traveling to? Is there a way for me even to go to all of these places without having to go back through another vertex twice? That's the Hamiltonian cycle. That's a constraint satisfaction problem. That is something I can do with backtracking. Now, traveling salesperson problem takes this Hamiltonian cycle and optimizes it. It says, I want a Hamiltonian cycle, but I want the shortest possible Hamiltonian cycle. Or we say the Hamiltonian cycle with the least weight, because I think of edges as having weights, and those weights in this particular instance represents distances, but the Hamiltonian cycle with the least weight in graph speak is what we're looking for. This is an optimization problem. That least weight makes it optimization. Here's a simple illustration of it. We've got this 6-node little city here, A, B, C, D, E, F. The goal here is to find the tour of minimum length starting and ending at the same city, and we're going to call A home base. So let's start there, visit all the cities. I need power. And we're back. All right, so having a look at this A, B, C, D, E, F, I just need to start at A and get back home. I can go let's go counterclockwise. A to E to D to C to B, and I go down to F and then go over to A. So this is my actual TSP for this. This is my optimal one, and this is we'll just show the answer here at the beginning just so we've got an idea. This is something that we can use the human calculator to just look at these edges. So if I figure out I've got to cut into the middle somewhere, and it turns out if I can cut into the middle where the longest outside edge is between A and B, I might find an improvement, and that's how I do it. So that's the way that I get this one. I cut out any other exterior edge, it costs me more to do so. So this is my TSP solution to this one. It goes A to E to D to C to B to F and then back to A. Or I could go clockwise, A, F, B, C, D, E, A. Same solution. It's just leaving the house going to the east one trip, leaving the house going to the west. All right, so there's the answer. Let's look at how we track this down. The TSP actually is an NP hard problem, and this is a class of problems that we know we're pretty sure, very, very sure, that there's no polynomial solution to this, right? So this is a problem that we have already determined is not going to have a polynomial solution. That's what the NP, there's no polynomial solution. At least that's the way I always remembered it. And this little example here comes to us from Waterloo, which has an entire page dedicated to the TSP, and there's a lot of cool stuff you can learn on there. It's good to learn. So it's math.waterloo.ca/TSP, and on it we see that the state of the art back in 1954 was solving TSP problems with the calculating power we had back then was about 49 cities. That's not very many, but it worked for that particular salesperson. Then in 2004, we've got this tour of Sweden that I think gets you to everything that might be city-like or town-like in Sweden, all 24,978 of them, and it's optimal. You can't get to all of those locations any shorter than that red collection of lines and vertices over there. So that's kind of the state of the art. It is gone. If you go look at that site, you can see some. They've got some solved 80,000 point solves. They're pretty impressive. But let's look at TSP with backtracking. And remember, backtracking is just finding is there a way to do it? Sure, there's a way to. There's a bunch of ways to get there, right? So we'll start at our first decision at A, and A having 3 neighbors, E, F, and B, gives me a tree that comes out of A, if A is my first thing here, and then I've got 3 things to place after that. And my window needs adjustment here, sorry. There we go. All right, so after I've chosen A, this is where I'm starting. It's not even one of the things I have to choose. I'm always starting at A, and that's one of the things you can do on Project 4 as well. Make sure that you lock down your starting location because you don't need to permute the starting location. Home is home, it always will be. After I've chosen B, E, or F, there's a decision tree below them. So if I go from A to B, I've got 2 choices, C or F. That's without me revisiting something that I've already visited. And we see that I can come around A, B, C, D, E, F, A. That's my most lexicographical solution, and it ends up solving it in 26. This backtracking thing works me through all the possible solutions. Over there, the fourth one in, if we follow that path, it goes A to B to C to F to E to D, which leads me to a dead end because now I can no longer access A. So this would get pruned by backtracking because it would lead me to a constraint violation. The only way to get back home is to visit another city twice. So that's a pruning that happens. Another one that happens a little bit earlier on, A, B, F, D, as I go to C or E, I see that I push myself into a dead end as well. So those get pruned. See, the earlier we violate a constraint, the more we prune from below them. So this is just backtracking, and this has enumerated all of the possible solutions that I can get there. And along the bottom, I see their weights. I see one for 27, there's a 31, a 33, another 27, 20, a couple of 27s more, another 20 again, and then a 33. So some of these are just the same solution. There's not a whole lot of solutions to this puzzle, right? We've only got those 5 edges around the outside that we can get rid of. So there's the 5 edges that we can get rid of and still make it back in. We've got those, and we've got the reversed versions of all of those. And so I think that's where we get all of those solutions from. Now, let's apply TSP here. TSP, sorry, let's apply B and B to the TSP. So I'm going to come along like I did in the previous version. Go A, B, C, D, E, F, A. Wow, I've got a solution there that's 27. Now this is my first solution. This is my upper bound. Anything that looks like it's going to cost me more than 27 isn't a violation of maybe the rules, but it's a violation of my work ethic because I don't want to work on something that's not going to give me anything, right? So I'm going to say this is going to be my upper bound. I'm not willing to do any more work than 27 from here on out. All right. The next thing, I'm going to backtrack a little bit. Now I'm going to start at A, B, C, D, F. That's me backing up a decision. So A, B, C, D, F, if I total those things in the graph, I'll see that's a weight of 23. Okay, 23, and then I've got some magic estimator function. Pay no attention to the magic estimator function. I'll clue you in on that later. But my magic estimator says it's going to take me 8 more work to finish once I've gotten from A to B to C to D to F. 8 more work plus the 23 that I know it takes to get there. Well, that's 31, and that's not less than 27. I'm pruning that. I prune that off, and then I go back up higher in the tree. How about A to B to C to F? Well, that's a cost of 22, and my magic estimator function says, well, once I get to F, I want to finish this up, it's going to cost you about 9 more. 22 plus 9, that's also 31, is also not less than 27, also getting pruned. Snip. A to B to F to C. Now that's pretty short. That's a 21 with an estimator that says there's only 6 more work. But guess what? 21 plus 6 is not less than 27. It's actually equal to 27, but it's still a waste of time because it's not an improvement. I'm looking for the absolute best. If I've got a 27 here, a 27 is a 27 is a 27. A best is the best is the best. There's no need investigating anything that's going to find me 2 or 3 or 4 any more than 1 copy of the best is just a waste of time. So I'll prune that. I've got some dead ends that I run into, A to B to F to D. So those get pruned from normal backtracking. I don't even have to involve their cost. But we can see here that we do end up, after we have tried everything, we've backtracked through all of the options from A to B and everything below that. So then I backtrack and try, well, what about AE? AE, DC, BFA gets me all the way down to the bottom with a new best score of 20. Now, that's 20 is definitely an improvement over the 27. I'm going to say that's my best. And everything from here on out that does not give me improvement over 20 is going to get pruned. So as I backtrack, I find AEDCF, that's a 14, and my estimator says there's only 10 more to go, that's a 24. Would have been great back here when I knew the 27. But now that I know the 20, that 24 is a waste of time, so I prune that as well. AEDF gives me an 11, plus 9 more work, that's a 20, that's not an improvement, still pruned, and so on. So we see that the better I get to estimate here, on the far side, I go from A to F, in just 5, and my estimator says, well, there's 15 more work to be done, but 5 plus 15 is not an improvement over the 20 that I already have, so let's prune it. And now I don't even have to investigate much of anything at all over there. So the earlier I can prune, obviously, the less work I do. This one we see finds our goal of having our optimal TSP here, our optimal Hamiltonian cycle here of length 20, and that gets it through A, E, going left to D to C to B to F, and then A. That is TSP. Now, I mentioned that there was this magic function that gives me this perfectly good estimate. You will not always have a magic function. You will not always have a perfectly good estimate. In this particular version, this estimate was perfect. It was right every single time. Remember, I said it's okay to be wrong as long as you're wrong short and you're not wrong long. So if you're wrong short, meaning your estimate is too optimistic, then you won't prune the right answer. But if you're wrong long, then you may prune the right answer. So we have to come up with a way to get this thing. As I mentioned earlier, coming up with promising was the early challenge with backtracking. Now coming up with promising and a magic estimator is what makes B&B the challenge that it is. But every problem has some way to estimate what you've got to do, even if it's causing you more work. You say, well, I can only do this estimate if I do some quadratic thing. I got to do a bunch of comparisons. Hey, that's great. A quadratic estimate, if it saves me from doing factorial work or exponential work, I'm all for it. A cubic one is okay, right? It's okay as long as it's going to save me that work because it is pruning. So we said our bounding function had to be some estimate, and in the TSP case, in the minimization thing, I'm saying this estimate must be less than or equal to reality, because if it's greater than reality, it will reject a possibly good solution. The bounding function must have a complexity better than just continuing the TSP, which is let's try all of these cities in some order, right? So the remaining k cities, if I try them in all the possible orders, that's k factorial work. So if my bounding function is k squared is an improvement over k factorial, I'd be glad to have it. Now, let's check your 281 history. What method can we use to find the lowest cost way to connect k vertices? Wow, seems like something I've heard before. Now, this might be a little misleading. You might think, well, I can think of it, it's kind of tree-ish, but that's not very pathish. That's okay. It's okay to have an estimate that violates constraints, because we won't actually use the estimate in finding, the estimate won't be included in the path. We're only using it to help find the path. So if the estimate violates constraints, that's okay, as long as it's an underestimate still. Meaning that when I do this correctly, and I haven't violated any constraints, the reality is going to be at least as long as my estimate. So that's okay. Then, you know now, I've given you all the hints that you need. It's done in k squared time. It connects all the k vertices, and it has a t in it. Yes, it's the MST. Some vertices are connected, some are not. For only the unvisited vertices, I need to connect them together with the lowest possible cost. That's my MST. The vertices that are connected so far, I know the order of them. So I know it goes from A to B to D to G, and I can take those edges and say, that I can calculate. Now I need to estimate, how do I include the rest of those things, the C and the E and the F? How do I include all of them, right? The visited vertices, I'm going to put them in the order that they're in, and then the unvisited vertices, I'm going to estimate what their distance is, and I want to put all of that together, right? And it says here, this does consider a solution that violates constraints, but it's a lower bound, it's an estimate. Here's my example. I've got this A, B, C, D, E, F, G graph. So I've got this graph with 7 points. I've got a current path that goes from A to B, B to C. So I know that those two edges are going to be included in this particular estimate. So the question is A, B, C a good start? A to B, B to C, is that a good start? So I say, well, I've got the current path that goes from A to B and B to C. I can add those up. I can add that to my lower bound is then the combination of what I know so far. And then I have to estimate getting to all the rest of that stuff. How do I estimate getting to D, E, F, and G? Well, we said the best way to connect those things cheaply might be an MST. So this now doesn't look like a Hamiltonian cycle, but I don't care because it's an underestimate. and I only want this to go, if I turn this into something that is Hamiltonian cyclish, it's got to be no less than the length here, this MST, and most likely it's going to be longer than the MST. So if the MST is too long, then the reality is even longer, and it's also not going to work. That's why it's okay to have an underestimate that violates constraints. So this gray part, that's the MST. The black part, that's the current path. Now I need to connect those two things, right? And an MST, or sorry, a TSP, if you think about it, the Hamiltonian cycle, it's got n vertices, and I leave each place once, so I should have n edges. So if I've got 7 vertices, I need 7 edges. So far I've got 2 that I've definitely put in my path. I've got 3 from my MST. I need 2 more. I mean, I could do it with just 1 more. I could do it without them. But what does that give me? That gives me an underestimate that's too under. It's too optimistic. It says too many things are good, and I waste too much time looking at things that I could prune away if I got away from that. So this one needs 2 more edges, because if I can put 1 more edge in there, that's good. If I can put 2 more edges in there, that's going to be as close as I can to reality. And I like to call these things the arms. These 2 blue lines, they connect the beginning of the path, that's the A vertex, and the end of the path, that's the C vertex. All the other vertices in the middle, they're already fully connected. We don't have to worry about them. We only have to worry about the beginning and end of the current partial path. So I say A, I find the shortest edge from A to anything that's not connected. So all of those things over there, I find it. And then I find the shortest edge from C to all of the other things that are not connected. And I find that, and I add it up. That's my estimate. In this particular version, you see that A and C are both closest to D. That's just the way that it happened. It's okay if they're closest to the same point, because remember, this is not a constraint satisfaction we're trying to do here. This is an underestimate. So if they go to the same place, that's the shortest it could possibly be. I don't want to try to get tricky with this. Take whatever's closest to A and use it. Take whatever's closest to C and use it. If they're the same thing, that's okay. If they're not, also okay. The shortest is the important. So these 2 blue lines, which we call the arms, are the way that we connect the current partial path to the unvisited vertices. Those 3 things put together, that's your lower bound estimate. If the black plus the blue plus the gray is less than your current best, then it sounds like the black is a good start. Gen perms, we've seen this already, right? We've seen a version of gen perms in an earlier slide when we're talking about stacks and queues. This is a newer version of gen perms. And what it has is just, it's a slightly more efficient way to do it because of the way that it uses memory. It accomplishes the exact same thing as a previous one does in the exact same way algorithmically. It just uses different containers to get it done. So I've got gen perms call here in line 2. I've got gen perms call here in line 11. Gen perms comes with a path and a perm length. So this path vector holds all of the vertices that I might possibly use, and the perm length says how many of those vertices have I already put into the proper order. And those how many always start at the beginning. So if perm length is 3, then I would say that my path is indices 0, 1, and 2 in the vector, and everything that shows up after the thing, after in locations 0, 1, and 2 in the vector are the things that are not permuted, right? As I move forward with gen perms, you see that gen perms gets called with perm length plus 1. That's me advancing the solution. You see my call to promising there. You see my call to, is this a solution? It's not a function in this particular version, because I said usually solution is pretty simple. If perm length is equal to the size of the path, that means that all of the things that I'm trying to permute are already in there. Then I've got a complete path. Let's do something with it. In this case, you're going to have to figure out what that do something is. You might have to save it, you might have to compare it to something, you might have to do both, but you got to do something with it, because this is the solution part that keeps me from recursing indefinitely. Here's if promising. So this is a new ordering, but it's got all of the things that I need to do. I've got a solution extension, I've got a promising check, and I've got a base case that is solution check that gets me out of this. So this one takes a little bit more learning to figure out how it does it, but it does it by moving things into this new position called perm length. And so if I've got a perm length, say I've got these 6 items, right? I've got a perm length of 3. That means these first 3 are already permuted. and then I just have to repermute these remaining 3 before I figure out what the path that starts with these 3 is. Okay, so perm length says, well, perm length is 3, that means these first 3 items are the ones that are in it. So perm length of 3 says bad stuff starts here. It's not bad, but it's not permuted. So I can go from perm length to the end and try to figure out how to put those things into the permutation. And this swapping of things does that. It swaps something new into that perm length position. And oftentimes this gets hard to read because as you first look at it, you say, well, okay, I is equal to perm length. And then the very first thing I do is I swap perm length with I. It doesn't sound like it does anything. It doesn't. But it allows the rest of the algorithm to work very well. So it's not the greatest thing, but there's no way to improve the efficiency on it. The only way that I can improve the efficiency on it is say, well, if I is equal to perm length, then don't bother swapping it. But then it adds the conditional that I had to do over and over again in a way that I don't want to add a conditional. So one swap every once in a while with some item in itself is not bad in this particular case. So we swap something into that new position, then we extend the search, and then we swap it back. We put it back away to make sure that things are how we wanted them. And this is important for the rest of the algorithm to say, well, we've tried all of the things at this position, and then we can backtrack and try something else there. So this swapping on either side of this is what's good for that. Optimal TSP with branch and bound, right? Given these n vertices, we need to find the best path out of these n minus 1 factorial options. We're going to use gen perms. We can start with an upper bound that's infinity, or if you've got a fast way to calculate a path that's guaranteed, that's not shorter than optimal, that might work too. All right, so think about that. How might you come up with something that's not shorter than optimal, and then is also a fast version of TSP? So if we use that instead of our infinity bound, then we say, okay, well, that's the worst we're gonna do. If we can't find any better than that, then that's our best. But if we can find something better than that, I've cut out a lot of work because I don't have to look all the way up to infinity. I have to look up to this fast version of it. We're going to use this upper bound to prune the rest of the search, and we lower it every time we find a shorter complete path. We measure each partial solution. That's from the beginning of path up to the perm length indexed. 0, 1, 2, 3, 4 when I've got a perm length of 5. I measure that, it's partial solution, and then I estimate the remaining and say this is my lower bound. If the partial solution and its lower bound exceeds my current upper bound, snip, it's gone away. If we end up with some path that's shorter than the upper bound, I need to save it because later at the end I need to print it. And I never know when I'm going to find the best one. So if I don't save it when I find it, this is that part of the thing we said you do something with it. So if I find it, I want to keep it because later I want to print it. When the search is done, my upper bound has the answer. That is TSP. Here's our cover slide for the TSP look here. This is a nice XKCD. We see something brilliant here from Randall Munroe. It's talking about the brute force solution of this is n factorial. That's trying all of the positions in whatever orders I can come up with them in. The DP solution, one we don't go into in this course, is better than that. It's n squared times 2 to the n. That's actually faster than what we're going to be doing here, but it's a bit more complicated. So this is where we said earlier, there may be a more elegant solution, but without knowing that middle pane elegant solution, you can always fall back on branch and bound. So we're going to fall back on branch and bound and leave this DP solution to your research. Of course, you could lazily sit in your chair and in constant time, which is never leaving the house, you can sell over the internet. All right, that's XKCD. Check it out. We've got the N Queens demo, and I have talked and talked and talked. I am low on time here. Those of you who need to leave, feel free to do so. I'm going to keep plowing through here and run through this N Queens demo. You can come back and check it out. The source code is available. We'll let you pull that down and play with it. So back to N Queens here. We know that each row is going to have exactly 1 queen, each column is going to have exactly 1 queen, and each diagonal will have at most 1 queen. I need ways to represent that, and I can get that done in these 4 1D arrays. One of them holds integers and the other 3 hold booleans. So we're going to simplify this by studying a 4x4, and then it's very easy to extend this to any n after that. So here's my first vector or array of things. I've got the position in each row. So in the 0th index of this, it tells me where the thing is in the first row, and it turns out it's in the first column. So 1, 3, 0, 2 shows the position of the queen in that particular row. That's what one of these things does, and it's going to be called, in the solution, it's going to be called position in row. That's the name of the vector. Then I've also got this column availability vector that tells me whether or not the column has any queen in it. And this is easy to maintain because every time I place a queen, I can just go turn that true to a false. And every time I remove a queen, I can say, well, now true, that column is available. So with these two queens placed, I see that there's the first column is empty. So that's true, it's available. The second column has a queen in it. So we're going to say false, it's not available for any more queens. The third column is empty, so it's true, it's available. The fourth column has a queen in it, of course it's false. So that's what I'm looking at. Those are my two vectors. Now I've got this more complicated one, and this is where I check out my diagonals. Those kind of magenta, argue, pink lines there, those are the diagonals that we're talking about. And you see that there's more diagonals than there are horizontals or verticals. So in this case, I end up with 7 left diagonals, and that 7 comes from the fact that I've got 2 times n minus 1 diagonals. If you want to do an 8x8 board, you're going to have 15 diagonals. All right? So that diagonal is just like I did my verticals. The way that I did my column availability is going to be the same, it's going to be referred to the same way. I look at that diagonal, that's that first one, my left diagonals start in the top left and move to the bottom right. So I see that that first one is available. There's no queen on that. So that's why it's true in this first. The second one is false. It's that pink one that goes through the second row, first column, and first row, second column. It's got a queen on it though, so it is no longer available. If I try to place anything on that diagonal, the queen that's already there will threaten it. I've got 2 empty diagonals after that, so you see that they're true, they're both available. Then I've got a queen sitting there in that 5th diagonal, so that's marked as false. The 6th and 7th diagonals are available, that's good. What's nice about this is the math. The math says if I'm looking to place a queen at some row and column, if I just add the row plus the column, I can use that in constant time to look in this vector and figure out, is that diagonal available? So I was trying to place something at, let's go with something, how about row 3, column 3? And if we go 0 index, that's really a 2 plus 2. I add those two things together, I get a 4, and I go look in my 0, 1, 2, 3, 4. I cannot place something at 2, 2 because it will be threatened by a queen that's already there. That's my left diagonals. My right diagonals are going to work very similarly. We're going to start indexing at the upper right and work our way down to the bottom left. Staying alive. All right, so how do I find the index here? It's a little bit more complicated, but not much. We're going to do the row minus the column. But since that sometime can send us negative, we're going to add that n plus 1 and add n minus 1 to it. So that's kind of like modding this to make it go back around to stay positive. So all I have to do is add the 2 row and columns to get the left diagonal index. I subtract the 2 row and columns to get the right diagonal index with some savor there. But that does the same thing. I can see where I've got available diagonals, and so any new row or column I'm trying to place in, I can say, well, I know that this row is available because I'm doing this a row at a time. When I get the column, I can check the column availability vector and say right away, is this a place that I can do it? If that's good, then I can check the left diagonal by adding the row and column and checking if that's available. And if that's available, I can say, well, let's subtract the column from the row and then go see if that's available. And if all 3 of those things are good, that is a promising placement. Here's my promising function then. All I do is I take a row and col and say, if that column is available, possibly, but if that column is not available, definitely not. And available has just been defined here as true for those of you trying to figure out how this code works. So if that particular column is available, and that diagonal is available, and the other diagonal is available, then it's a promising placement. And that's how simple this promising is. It's elegant because we had to figure out how to go from 2D to 1D. If you had stuck with the 2D thing, you'd have written something with a lot of loops, and it would not have been nearly as fast as this. This is a constant amount of work, right? You can see that. We're just doing what? At most, four arithmetic operations, 3 lookups, and some logical conjunction there. Man, that's fast. That's a fast promising, and that's good because we got to do a lot of it. Usually promising gets called quite frequently. Here is our recursive put queen function, and what that tries to do is tries to put a queen in every row. So this is what we were previously in pseudocode land calling check node, because every time I'm checking a node, I'm really, in this solution, putting a queen on the board. So I need to have this recursive put queen in line 1 defined, calls put queen in line 15 defined there. And it calls it with the next row. So we call put queen with row, and then later on when we recurse deeper, we call put queen with row plus 1. That's going deeper in the decision tree. What else do we need? We need some base case. I need some solution check. If row is equal to n, I've put the last queen, the solution is found, we're out. That's my base case. Otherwise, I'm going to try to extend the solution, which has some for loop that's trying all of the options in that particular row wrapped around a call to promising. And that promising is going to be doing some check on that. And once it's promising, then we extend the solution, right? So if that row and column are promising, then I'm going to fill them up. I say, well, the position in that row is now that column value. That's putting a number in there. I'm storing that. I say that column is no longer available. I say that diagonal is no longer available. I say the other diagonal is no longer available because I'm trying to extend the solution. I need to reserve those so that when I try to go to the next row, they know where I put something in the row before, right? After I do this check, the remaining 3 lines here just completely undo what these lines 12 through 14 did. We place a piece in this row and column, check to see if we can extend the solution there, and then we remove the piece from that row and column. That's the way that it works. And then when we're looking at our Gen Perms version, we were swapping something to a position, trying to extend the solution, and then swapping it back where it belongs. So you have this feeling of doing something, trying to extend it, and then undoing it so the rest of the algorithm can work. That's the way that put queen works. All right? We've got this N Queens demo here. We're gonna go pull this up, and I gotta make sure that I got my terminal all set for me. I'll just take a new one. How's that sound? And get this done here with a duo thing. I'll give you a chance to go ahead and download this. Come on, duo. Oh, approve. Yeah, there we go. I approved. I approve this duo. My name's Marcus Darden, and I approve this duo. Okay. All right, then. All right. I've got to do a scene change. Give me a half a second here. Drop into studio mode. Go to Kane mode. Oh, that wasn't what I wanted at all. Come on back to me here. We got that part's going well. No. Okay, there we go. And one more thing, I need to take my terminal and pick up this one. All right, through the magic of television, here we are. So this is the N Queens demo. You can follow along with me here, and I will get that done for you. Let's make this screen just a little bit wider, though. I'd like to get that out to about 100. There we go. Makes it a little bigger. Okay, so let's SSH into Kane. I'm going to do that here. And what I'd like to do is go pull this stuff down just as it says in the slide. There. You'll see my keyboard down there. Hopefully you can see it. If I do anything tricky, you can follow along. All right, so let's make directory and queens. CD into that directory. That's good. And then I'm going to call wget bit.ly eeks 281-nqueens-demo. I'll put that into nqdemo.tgz. We've got it. And then now I can expand that. Tar extract z files. nqdemo as well. There's all my files. So if I do an ls, you'll see I've got my tar file, my tarball there, that tgz file. I got a couple of cpp files and an hpp file. Great. Now let's compile it. G++ minus standard equals C++1z minus 03. That's optimized for speed. Star.cpp. Output nqueens. Doing a listing there. You'll see now. Hey, wait. What is going on here? I see that my screen is not following me. I disbelieve. I don't know, folks. This is true. I thought I had fewer terminal windows. I guess I have way too many windows open. I was cruising along there. All right, come on, term. I can't even find the window that is being shown. Okay. That window does not exist. Yeah, I don't know, gang. I'm kind of stuck here. This won't change windows. Oh, it changed the window. Wait. Wait. There we go. Yes. All right. Sorry about that. I don't know what happened there, but it was painful. Okay, it looks like we're live. So, let's go to Kane. Make dir and queens. I'll CD into that thing. And then let's go from the slide here. wget bit.ly equals 281 and queens can spell. All right, so got it down, and there we go. I don't know what was going on there. I needed to do a reinstall of my terminal because it decided I needed an update at that moment. Here I have my tarball. I downloaded it. I've got those files in there. I've got 2 CPP files, an HPP file, and I can compile that. C++1Z minus 03. It compiles. Now I've got an executable here. That's this nqueens file. So I can call nqueens. Enter the number of queens. Let's go with 4. We've seen this. Let's display the results. It looks like there were 2 solutions. 60 branches were explored out of a possible 256 permutations. It looks like those 19 got me the first one, 60 gets me all of them. Savings of over 76% that I didn't have to look at out of what brute force would have taken to get to the answer there. All right, let's try it with 5 queens. Sure, we'll look at the results. I said, sure, we'll look at the results. 5 and yes. All right, looks like there was 10 solutions. 220 branches were explored out of 3125 possible permutations. Right, if I scroll back, I can take a look at those. We see some of the stuff in there. This one here looks like that's the n queen solution right there with just a queen wrapped around the outside. So that's some of my solutions. However, this one is a uniquely 5 queen solution there. That's not an extension of a 4 queen solution. All right, let's go bigger. How about 6? Sure, we'll look one last time. Right, 4 solutions and 6 queens. That's kind of interesting. It went up from 4 to 5 and then down to 6, but we keep having solutions. 894 branches explored out of 46,000. Looks like my savings is growing. At 6 queens, I've saved 98% of the search space. Let's take it up to 8 and not display all of those. There's 92 of them. 15,000 branches explored out of that 16 million. Savings of 99.9%. Life is getting good. Let's go big. Let's go to 12 queens. Definitely not displaying all those results. 14,200 solutions. And we found that after looking at some 10 million branches out of an 8.9 times 10 to the 12th possible permutations. Savings of 99.9999%. That's amazing. All right, there's no sense going big if we're not going big. How about 15 queens? Display the results? Nah. Now look at that, we've actually got a hitch there. It's actually doing some calculating, some thinking time there. That's going to take us a little bit of time here. It's usually on the order of 30-ish seconds or so. But there we go. Look at that. And this is how efficient backtracking can be. Look at that savings of 100%. Of course, that's just floating point rounding error. But we did look at some incredible number of branches, like 2.5 billion branches out of a possible 4.3 times 10 to the 17th permutations, and found 2 million solutions to this problem of 15 queens. Take a quick peek at the code here. There's our driver, and it doesn't do much, right? It does our user input. It creates a board of the proper size. You enter the number of queens. It asks you if you want to display the results, and then tells the n queens object that initializes here that the board is of size n. Do the thing. Does the solution and displays it yes or no, and then does the calculation. It shows how many permutations were checked, how many branches got checked, how many solutions there were, and this is where our math gives us our rounding error. But that's how the driver works. We jump over here to the actual C++ code. We've got that function we saw in the slides here. It's put queen. Put queen, as was discussed in the slide, works just like that. We see up at the top, we've got our constructor, and here's our promising function, lines 29 to 32. So this is good code to pull apart. We call put queen here starting in the first row. So that's why put queen is called with a 0, because we want to start placing something in the first row. When you're working with gen perms, you'll be able to say, well, I don't want to permute the first item. Let's start with gen perms at position 1, because I always want to start at home. I don't need to worry about how many different ways can I start this. Okay, so you'll have some options there. All right, this is the put queens demo, or the n queens demo. Lunchtime. Sorry for the overage there. We'll see you on the other side.